Hello, everyone. My name is Chenji, and this is Lianghong. We are from Pinterest story caching team. Today, we're going to present our works in past year, which is mainly focused on HBase in multi-cell and the efficient backup for HBase. So today's agenda, first, I'm going to go through like the current scenario for HBase in Pinterest, and then I'm going to talk about like our multi-cell work in HBase. And multi-cell is like, since Pinterest in AWS, it is called a cell origin, but you can in general think as a data center. And after that, Lianghong will present his like work in efficiency backup. So Pinterest started to use HBase for online service since 2013. It is used to backup like core service like Zen UMS, and Zen is like Facebook's style, which is deal with like the graph-related data, and the UMS is just simple key value. We have around like 50 HBase cluster running on 1.2 revision, and we just finished upgrade like in past like 3 years, I think, or 2 years. We have our internal build for HBase, which support like the STG, CSS map, off-heap bucket cache, and some timestamp feature. These are all the patches either we develop ourselves or like grab from other higher version revision. So why want to do multi-cell? First, like we've been working on internalization for the past several years, and now over half of our active users are from out of states. So to provide more reliability and with lower latency to local users, we decided to explore the multi-cell architecture for our infrastructure. So here's our basic architecture for Pinterest. So let's say this is a US East and US West. So we have a global load balancer managed by our traffic team. So when you open your Pinterest app, and so basically the global load balancer will pick up the closest like region for you, and the forward traffic to the either US East or West. So in the local side, the local load balancer will just forward traffic to front end service, and all the way to our data service, cache, and database. So we except data service, and data service and database, there's not allowed like, any cross-cell traffic. So so we provide actually 2 patterns for different consistent level table level. So you can mark your case as like either you need a master or master slave. Master, which is also called like sometimes alive, which means like both cell can take the right traffic. And you can see from the graph here is like either US or West will take the just right traffic and pass to the data service. Data service will update the database and then invite the cache. And the database just replicate a through replication flow. This is actually the master is like very common for most of the cases. Like either I think most of the key value will just do master because there's no there will be no conflicts or keys among keys. And this replication is like basically bidirection replication. But for cases like which need a stronger consistency, which to avoid conflicts, like for example, in the cases we can compete for like the primary key, like say email and account sign up. In that case, we cannot allow like master because like well database cannot like solve that conflicts. So we provide another pattern which is called master slave. So here, let's say for example, if the West is the master, and if write traffic is go to the east side, and the data service will forward that write request to the remote peer, and the remote peer will update the database, and the other one-way replication direction replication flow will replicate data back to US East. And here we have another concept called remote marker. After like the data service got the response from remote peer, it will set a remote marker. Remote marker means here like the data related data is actually out of date in local DB. which will be used in the read next time. So in this pattern, when we read it, like it will first check the remote marker. If the remote marker is set, it means the local DB is out of date. So it will forward the request to the US West to read the latest data from the US West from the master. So remote marker is set with TTL here. So basically, like the remote marker will be cleaned eventually after expiration. So if anything wrong happened to like clean the remote marker, and but like it's very hard to tune a static TTL since like if you're thinking about a too long TTL, will introduce like extra traffic to cross sell, and which will be more cost. And if a lower TTL, we just like your like markers may be cleaned before like a replication arrived, so the consistency is not guaranteed. So to avoid that case, we introduced another service called cache invalidating service. So besides cleaning remote marker, the cache invalidating service will also deal with like the cache consistency, which is like the local consistency between cache and database. So you can think about the other case, right? Because in either case, like if the other write happened in another cell, right? And since we deal with the cache logic in the data service, if a write happened in the US West, and since the West service has no context on this request, so it will not be able to clean the local cache. So we develop a cache invalidating service. Like here, you can see we publish the database changes to Kafka, and the cache invalidating service will consume the Kafka events. And you will just invalidate the cache, and also the remote marker, as long as the replication flow arrived and will be published and publish Kafka event. So we provide actually customized like cache mapping logic. So user can write in their customized mapping logic based on the any DB changes and find out which caches you need to invalidate. So with cache invalidating service, we can guarantee like as long as like the replication arrived, we can be able to invalidate cache and also remote marker, and all the read traffic can either can read the local database. So previously we talked about our general multi-cell architecture, and but we haven't touched about how it embedded with different like database engines. So here I'm going through like how it works, and so MySQL and HBase is the two major databases we use for our online service. So actually, when we first designed this architecture, it's mainly based on MySQL because MySQL is very friendly to this architecture because Facebook already explored a similar idea with MySQL, and we can just simply adapt some like open source project like Maxwell and Maxwell like MySQL's feature like comment. So let's see. You can think here the previous graph like this part. This actually requires basically a system like you should publish your database changes to Kafka, and with also some customer information in the Kafka event. So like Maxwell is like the if you're familiar with the Maxwell is just a daemon like which is running on the MySQL instance. We can publish the tell the bin log and publish the bin log to the Kafka. And MySQL comment is a feature which you can add some customer information on the SQL language, SQL query, and it will be part of the bin log, but it will not be stored in the actual data. So to make HBase also adapt with its architecture, we also developed a similar stuff like so the Maxwell corresponding to we call the HBase replication proxy. And the MySQL common corresponds to HBase annotations. So HBase replication proxy is basically like we'll publish the Kafka event, and annotations allow the similar feature like comment. You can basically add customer information in the write request. So first, the HBase replication proxy. So we call it HRP here. HRP basically it works like a fake HBase clusters, but instead of writing data to the Warlock and the mem store, this service just like publish the data to Kafka. The proxy explores the HBase replication API, so it is simple to use. You can just set a replication peer for cluster A and cluster B, and the multiple HBase cluster can share the same proxy. And we allow like customized Kafka topic, so you can basically customize your Kafka topic based on cluster name, table, and family. And so each actually Kafka event is corresponding to a mutation, a mutate in HBase. And yeah. So HBase annotations, it's like, we change, it's a part of the mutate. So it will be written in the Warlock, but not in the mem store. So here is kind of one of the example of the Kafka event. So you can see like the data is the row key, table, operation. This is the delta is a change. This is base 64 encoded. So, and also like this is part is the annotation we added. This is the customer information about this data type and some like forward request ID. Yeah, so HBase replication service, the proxy we mentioned about, it will just take care of like convert the annotation as part of the Kafka event. So the consumer can get the customer event, information they added before. Oh, another thing we did for HBase specific is the timestamp. So so in Pinterest, HBase is used for like more write-heavy online service. So it is more likely the risk condition will happen. So like we actually changed the HBase protocol to ask the HBase return the timestamp when doing the write or the mutation request, so that like either invalidate the cache or clean the remote marker, we can just compare timestamp to make sure which one is the later one. So another issue we met in the multi-cell environment is the replication topology. So our original idea is just set up this simple replication flow. So we actually have, in the multi-cell, we still have 2 clusters in each cell, just in case like, so there's actually 2 kind of failover in Pinterest. Like if you do global fail, it's just like failover, just like fail the whole traffic to one cell. But this is pretty heavy because all the front end service will be affected. Another failover, just local failover, is like you just failover the local master and slave, and just for some operation, daily operation. So like, so we set a replication like here, but like this topology has an issue is like, so sometimes like if we like there's 2 clusters in each cell, 1 cluster in each cell has a trouble. Like this replication flow is just basically blocked. So to prevent like this like happen, we just set up like this like fortress to 6 links. But this is pretty heavy because things like each request will be replicated like to the same cluster 3 times. And there's like 4, I think 4 links, 4 cross-cell links. And this wastes a lot of resource and cross-cell traffic. So we have a new idea is basically just we set up a zookeeper proxy in each cell, and in each cell like we will register like the master reading server to that zookeeper. So based on config, like the zookeeper will just every time you do a failover, and the master will update the zk service with the master's region servers. And since HBase replication is based on peers, so even after the update the region server, it will continue the replications. So like for the intercell, it's just like the master will just set up the replication to the remote like zookeeper proxy. So we avoid like the 6 links. This is still in testing, so we will have more results in future. Yeah. So next, Lianghong will talk about like how he improved like our HBase backup process in Pinterest.
All right. Thanks, CJ, for introducing multi-cell work. So as another mechanism to improve reliability at Pinterest, we back up data periodically to S3. So the overview of my part is that I'll first briefly give an introduction about how we used to do backup at Pinterest, and also describe how we simplified the backup pipeline. And at last, I will describe an offline deduplication tool that we developed to significantly reduce the S3 storage capacity on. So to first give you a notion of how Pinterest used to do backup, as CJ mentioned previously, HBase serves highly critical data. As a result, it requires very high availability. So to be specific, we have tens of clusters with tens of petabytes of data. So despite the high availability of HBase itself, we still perform this daily backup to S3 for disaster recovery purposes. And to be more specific, we do backups of HBase snapshots as well as write-ahead logs for point-in-time recovery. And we also maintain weekly and monthly backups on top of that, according to some predetermined retention policy. So in total, we maintain roughly around 15 copies of backups on S3 for each data set. So the snapshot data is not only used for disaster recovery. Our client teams also use this data for offline data analysis jobs. So we need this data to be available. Before we dive in, I want to note that for historical reasons, Pinterest used HBase version 0.94. So when we first developed the backup pipeline, and back then, HBase, that version doesn't support direct export to S3. The only supported method was to export from HBase to another HDFS cluster. As a result, our original backup pipeline consisted of 2 steps. So the first step is to export HBase table snapshots and walls to a dedicated backup HDFS cluster. And the second step, as you can see, is to upload the data from the HDFS backup cluster to S3. However, we noticed the problem that as the amount of data, like on the order of petabytes, grows over time, the storage cost on S3 increased significantly. And we have to keep adding capacity to the dedicated HDFS cluster to keep up with the pace of data increase. And this caused us not only infra cost issues, but also operational pain. So recently, Pinterest has completed a HBase upgrade from version 0.94 to 1.2. So along with numerous performance improvements as well as bug fixes, it also comes with a very handy direct export table snapshot to S3 utility. So taking this opportunity, we optimized our backup pipeline by removing the HDFS backup cluster from the backup path. And in addition, as you may notice, we also created a tool which we call Pinterest, which asynchronously deduplicates redundant S3 snapshots data to reduce the S3 capacity usage. And we will talk about that later. So one major challenge we encountered in the migration was how do we minimize the impact on our production HBase clusters. Since these production HBase clusters serve online requests and backup is usually a resource-intensive job, we want the interruption to be minimized. So the table export process is done using a job that's similar to DIST-CP, but it's our internal variant. And to make it faster, we use the S3A client with the fast upload option. But there were a few issues that we noticed, and the most notable issue we noticed is that directly S3 uploads tends to be very CPU intensive, especially for large H files. Reminded that a HDFS backup process is basically copying the H files on a local HBase cluster onto S3. You might think that this might be counterintuitive, but actually transferring large files requires a lot of computation. And this is specifically because for large files, they are first broken down into smaller chunks And for each small chunk, we need to they need to be hashed and signed before uploaded to S3. So to overcome this issue, we had what we did is we constrained the maximum number of threads and yard containers over host, so that during the during the backup process, the maximum CPU overhead during backup is less than 30%. We also schedule the backup to run during the off-peak time, so that it doesn't interfere with our production workflow. So next, I will talk about how we did offline edge file deduplication. And this idea actually is inspired by the observation that large edge files actually rarely change across backup cycles. So while incremental backups updates are merged with minor compactions, the large edge files are only merged during a major compaction. So as a result, adjacent backup dates, they usually contain many duplicate files, and especially for read-heavy workloads. So based on this observation, we have proposed and implemented a simple file-level deduplication tool, which we call pindedup. What it does is asynchronously checks for duplicate S3 files across adjacent backup cycles, and it replaces the older files with references to the newer file. So let me briefly illustrate how pindedup works. So it takes two parameters. Let's say it's the source location and the target location. These are two S3 locations with adjacent backup dates. Let's assume that we for simplicity, what pindedup does, it traverses the directory hierarchy in the HBase directory, and it identifies the set of edge files under each region. So in this example, let's suppose we're talking about region 1, let's say RS1. It has 3 edge files, F1, F2, and F3 in the previous day, and F1, F4, and F5 in the next backup day. As you can see, after 1 day, the smaller files are changed because probably minor compaction happens during the writes. But the largest file, which accounts for the most storage usage, is usually not changed because it is changed only when a major compaction happens. And the opportunity here is that as long as we can identify this large file that is not changed, even if there's only one file that didn't change, we can still save a lot of space. So what we do is we check for the same. We only claim a file to be duplicate when the file name as well as its checksum matches. And this approach is actually quite simple. There's no need for on this dedupe index, because the dedupe index is really small and the lookup is really fast because you constrain the deduplication scope into a single region. So despite the simplicity of this tool, there were several design choices that we have to make. I will mainly talk about the following 3. So the first choice we had to make is whether we do file versus chunk level deduplication. So the natural question that came into mind is, now, can we use a more fine-grained deduplication technique such as chunk level dedupe to get more benefits, or to further reduce the S3 capacity usage? And the answer is actually no. And we observed that we can only obtain very marginal benefits from chunk level dedupe. We actually implemented a wrapping fingerprinting chunking algorithm with an industry kind of standard 4 kilobyte average chunk size. Although this increased complexity for implementation, we initially expected it will improve this, the deduplication ratio. However, it turned out that it's not the case. So let me give you an example why. Let's say before compaction, for simplicity, I'm only talking about 2 files, and I'm talking about what happens during major compaction. So before major compaction, let's say we have 2 files, and there's a large file, and there was a smaller file to be merged in. And after compaction, what we observed is that during compaction, the merge changes are spread almost across the entire file sparsely. As a result, when we are doing a chunk level dedupe, for example, we are taking chunk boundaries inside those files, what we observe is that most of the chunks are modified. As a result, you couldn't easily find a duplicate chunk. So the conclusion is that file level deduplication is good enough for HBase backup. And we, to make deduplication more effective, we also tune our major compaction to be less aggressive, so that it only does major compaction when it really needs to. The second choice we had to make is whether to do online deduplication or offline. So by online deduplication, I mean the deduplication happens before data is uploaded to S3. And this could potentially reduce the data transfer, because the data doesn't need to be transferred if it will be deduplicated. However, we choose offline dedupe because the most reason is because it allows us to control when deduplication occurs. So since our client teams often use snapshots for their offline analysis, we could delay the deduplication until when the analysis jobs are finished. And the second reason is that doing so also separates the backup pipeline with the dedupe pipeline, so that dedupe fail doesn't cause backup jobs to fail. And it's easier for engineers to identify the problems. And the last choice we had to make is whether or not to keep the latest version unmodified. So when identifying two duplicate files, there was an important question, which is whether to replace the older file with the reference or to replace the newer file. Actually, let me go through a quick example, and I'll try to explain why we choose to replace the older file. So actually, the more intuitive version is to keep the more intuitive approach is to keep the old file unmodified, since you don't need to touch old data and you only need to write new data. In this example, we call it backward dedupe chain. And let's say we have data, backup data from day 1, day 2, and day 3. And these are all duplicate files. If we choose to replace the newer file with a reference to the newest file, the advantage is that during the decoding, for example, when I'm accessing F3, I only need to decode it once because it has a direct reference to the older file F1. However, it has a dangling pointer problem. So for example, when the older files are deleted due to a retention policy, let's say F1 is deleted on S3, then F2 and F3 becomes unrecoverable, and this will result in a problem. So the approach we take is what we call forward dedupe chain. In this case, we keep the latest file unchanged, but replace the older file with the reference to the previous peer in the backup cycle. And as you can see in this example, there's no overhead accessing the latest copy because the latest copy is unmodified, and it also avoids the dangling pointer problem. I have to point out that we are making the trade-off that when you are recovering the older file, say F1, then you have to decode once. But usually what we observe is that users mostly only access the latest copy. So this hasn't been a problem for us. Okay, so just to give a quick overview of the results we have achieved by this improvement, we were able to reduce the backup end-to-end time by 50% because we removed the intermediate backup cluster in the in between, and we were able to achieve significant, like up to 2 orders of magnitude reduction of S3 storage usage. It also reduced the infrastructure cost and operational overhead. And thank you very much. So I'm not sure if we still have more time for Q&A, but yes, we are hiring. Okay. So I think we still have 5 minutes for Q&A, right? Sure.
Hello? Oh, yeah. So this is basically, so we basically implemented the same protobuf protocol with like the replicate API. So, and also it works as like a internal So it will just like it will also register the service in the Zookeeper cluster. So it will be just the same as just you add the replication. You just add a peer and the Zookeeper nodes, yeah, and it will send the replication traffic to that service. And instead of just like writing to Warlog and the memstore, it just publish the like replication request to Kafka. Yeah.
Similar question, just trying to determine kind of how you guys modify some stuff. The change for annotations and timestamp. I was wondering, are those protocol changes then from your client side as well to send the annotations in as to what type of operation it was, and the timestamp similar change to the protocol from the server?
Okay. So for the timestamp, we have to change like the server-side logic and also the protobuf, like both client-side and the server-side. And we changed that for both the HBase native clients and the asynchronous client. Yeah.
For the HBase proxy that you were talking about, why not just use the coprocessor instead? Like hook it up in some kind of coprocessor after you finish writing to the wall and writing to the memstore?
Oh, so first, like we actually want to like to be in real time, and also like we want to minimize the impact on the online clusters. So we think the replication is like pretty robust and the minimize the effect on the cluster itself.
Yeah, but
so
you
it's
still
like
won't be in the actual write path, right?
Mm-hmm.
It still is not in the actual write path, right? So it won't directly affect it.
No,
It still has to do work for writing the replication log to somewhere else, right?
yeah.
Like apart from that, why not just like instantiate a Kafka consumer right over there and send the data to your Kafka consumer
Oh, you mean
or
right?
to your Kafka cluster, basically?
That you mean directory?
Yeah.
You mean sending the?
Yeah, the wall thing.
Oh, you mean tell the Warlog? Or
Yeah.
just, but Warlog have the flush time, right? Or like not like just like but you have to deal with like the any kind of exception logic, right? It's basically the same logic which is already implemented in replication, right? Right, like split the logs, like all these kind of things. You have to deal with, detect all these kind of things. This is original design. We want to implement the same thing as like tell the bin log. We want tell the Warlog, right? But I think like there are a lot of like edge cases you have to deal with, and we found like all these cases is already taken care of by the replication. So we just use that, like
Oh, okay.
yeah. And also this is much simpler. Just like it's just as simple as to add a replication peer, yeah, to use. Okay.
Hi. In one of your slides, you said you upgraded from 0.94 to 1.2.
No,
did you
9.4 to 1.2.
1. Yeah. So did you face any challenges? If so, what are they?
I think last year we had a talking about this. So I think the mainly like it just but I'm not sure if we can kind of find the slides last year online. But like the mainly just we want to we're doing the migration without any downtime. So we have do a lot of things like just we do it very slowly and backup and just data migration stuff like
To add to what CJ just mentioned, I think Tianying, which is also from our team, presented last year, and she also has engineering block. So I think
you can probably find that.
Yeah, so it has more
online,
details. We use some special replication mechanism to make sure that there's no issue between like different versions.
Okay, cool. Thank you.
Thank you.
Cool, thanks.